Hello, welcome everyone. I'm Brian Borum, I'm the track host for this session. I have done a little bit of networking myself, but you're all here to listen to the speaker here, so let me introduce Rastislav Szabo.
Yeah, thank you. Hello everybody. So I'm Rastislav Szabo, and today I'll be speaking about network observability with IPFIX, Prometheus, and Elasticsearch. Before I begin, something about me. I'm a staff engineer at Pantheon.tech. We are architecting software solutions, mostly for networking industry. Previously, I was mostly focused on network manageability, using netconv and YANG protocols, currently working on cloud-native networking projects. And I'm contributing to several open source projects, such as Sysrepo, which was netconv YANG related, FDIO, mostly in the GoVPP sub-project, and Legato and Contiv-VPP. They are cloud-native related projects, and I'll be briefly talking about them during my talk as well. So, let's start with some motivation. Why do we need network observability in Kubernetes? Well, I would say that many Kubernetes cluster operators do not care too much about the networking while everything works as it should. But at the very minimum, you would at least need to be alerted whenever there is some networking related problem in your cluster. Either some fatal issue or just unexpected congestion or a packet drop. And that might be just between the pods on a node, or even in the fabric between the nodes or in the underlying network. Apart from network failures, another motivation would be identification of the bottlenecks. In case you want to distribute traffic in the cluster so that everything works correctly, you usually want to see whether your network would properly handle your load distribution. And of course, in case you are doing large-scale deployments, you want to know where are the limits of the scale. Another motivation would be detection and investigation of malicious activities. For that, you of course may need to, for the detection, that's quite easily doable. For the investigation, you may need a little bit more data than usual. And since I'm an engineer in the field of cloud-native network functions, which is network functions built as a set of microservices. For instance, a firewall or carrier-grade NAT running in a Kubernetes cluster as a set of pods. For those use cases, everything what I have just said becomes even more important. So now knowing the importance, what are the current options for network observability in Kubernetes? I would say it's metrics everywhere, right? Pretty much every piece of everything that you deploy in your cluster exports some metrics. And the same is true for the networking. You have CNIs that export metrics. Actually, only few of them export the metrics that are useful for the observability into the network itself. Some of them just export some internal counters of errors, of programmed interfaces, etc. But for instance, not packet rate on individual interface of a pod. Another option would be service meshes. Of course, if you are using service mesh, you get a lot of visibility, but mostly on the application layer, not into the lower layers of the network. But for instance, Istio can support even TCP telemetry data, and you can collect that with Prometheus and display. The third option would be doing the metrics yourself. You can do something like your own monitoring tool, which would monitor each one network namespace of each one pod that is running in your cluster and export the statistics on the interfaces. That's a bit of work, of course, and brings some challenges as well. But the most important point that I want to mention in here is that metrics may be not enough. Let's imagine that, okay, you have this actual example of a CNI called Contiv-VPP, which provides Prometheus metrics for each one pod interface. You can display packet counters, byte counters, packet drops, and that kind of data. You can get all of that into Prometheus. You can display that in Grafana, for instance, as shown here. But the issue is that in case of, let's imagine that you have a security incident in the network, you can easily spot that something is happening in the network, right? You have a spike in the graph, but you cannot really tell what is causing the issue. You don't know from where the attacker comes, what is the actual traffic which he uses for the attack, etc. So for that, you need a little bit more data than just metrics. And if I said that metrics are not enough, so what would be a solution of the issue? In traditional networks, we used protocols such as Netflow and IPFIX. I would just ask how many of you have used Netflow or IPFIX in the past? Okay, like 1/3 of the people here. That's nice. So for the rest, what Netflow and IPFIX essentially does, in traditional networks, you can enable that feature on a router or on a switch in the network, and the router would collect some most important information per each flow in the network, such as source and destination IP address and ports, type of service, interface through which the flow passes, of course, packets and byte counters, and timestamp information. The flow exporter, in this case a router or switch or a specialized hardware probe in the network, would just send this information per each flow into some flow collector, which would be a dedicated component in your network. The collector is responsible for retrieval of these informations, their preprocessing, and storage. And the third component in such a deployment would be some analysis tool, which pretty much accesses the data stored in the stored by the flow collector and shows either some user interface or gives ability to search for some particular data. I also need to say that these flow collector and analysis tools are often commercially sold products, but there are also open source options. Okay, so how we can use the same principles in Kubernetes? Well, in Kubernetes, what is actually a router or switch in the deployment is a CNI plugin. It pretty much either switches or routes the packets between the pods on the same node or between the nodes. So the CNI plugin can provide this data. CNI plugin is actually the only correct place from where we can get such data, because the traffic between the nodes is often encapsulated into some tunnel or something similar. So you cannot really export those information using the switches and routers that you would have in your local network between the nodes. And as a collector analyzer, we can use something that would be cloud native, such as the Elasticsearch, which is a shortcut for Elasticsearch, Logstash, and Kibana, 3 open source components, which go together and they create a whole ecosystem. From these three components, Logstash can be used as a flow collector. It supports IPFIX, Netflow, and Sflow processing. Elasticsearch can be used as the storage plus the search engine for the flows stored in the Elasticsearch, and Kibana as the analysis tool or the UI which you can use to access the stored flows. I'll show you a demo in a while where I will enable IPFIX in one CNI, and the CNI is called Contiv-VPP. The CNI is primarily focused on cloud-native network function deployments, since it uses FDI or VPP as the data plane. Essentially, it is a forwarding something like a router and switch functionality in a user space process that runs as a vSwitch on each node in the cluster. It is very high performant. It uses something called vector packet processing, which means that it can forward a whole set of packets instead of a single packet in each operation. It provides kubeproxy functionality all on VPP, so kubeproxy is actually bypassed there. And it also provides a special type of interfaces called MEMIFs, which allow a packet to traverse from a pod into the vSwitch through shared memory. And the best news is that it already supports IPFIX, so it pretty much needs to be just enabled. For the demo that I'll show, I have enabled it only through the debug CLI of the VPP, but for a proper implementation, the process would go as shown here. And I think that eventually we'll be able to upstream that into the CNI. So first we need to write a plugin into the Contiv CNI, which is quite easy. It is easily extendable. The CNI programs VPP through a management component called Legato.io VPP agent, where we need to add IPFIX support. That's actually work that is already in progress. And this Legato VPP agent is able to enable the IPFIX on each of the pod interfaces. Okay, and as the flow collector and analyzer, I mentioned that I'll use the Elk stack. Luckily enough, I found a project called Elasticflow, whose author is actually sitting in the audience, which provides all the REST glue that needs to be used in order to build this solution. Pretty much it is a set of codecs and filters in the Logstash and the dashboards in Kibana. So all that I had to do was actually package this into Docker containers, deploy into Kubernetes, and configure the CNI to send the flows into the Logstash pod as shown in the picture. What you can also see is a list of pods. So as I said, Elasticsearch, Logstash, and Kibana are just 3 pods running in the system. This is a result of such a deployment. I'll show you this on an actual running system in a second. So this shows the flows between pods in the cluster. The cluster was just very simple, few kubedns pods and the Elk itself. Then you can see the different conversations between the pods, so the clients and the servers, and these are the individual flows. But let me go actually into my VM, where I have this running. Okay, so let me first go into kubectl as you can see, the Elasticsearch, Elasticflow, and Kibana are running as pods. Apart from that, I have one job, which is Elasticflow Kibana setup. It just pushes some configuration into Kibana when it starts. Apart from the Elasticflow, I have the Contiv CNI running on the node. It is just one node cluster, so only everything what you see here is actually running on this node.
Can you make that bigger?
Yeah, sure. Yep. As I have told you already, the Contiv-VPP CNI runs the VPP vSwitch on each node. I can show you that. So this is the VPP instance, which acts as the vSwitch between the pods. These are the individual interfaces that go towards the pods. You can see a lot of packets coming through them. And these are the flows that are currently seen by the VPP and exported into the Logstash. So let's go back into Kibana, which, as I said, accesses the flows which are stored in the Elasticsearch, and they were stored into the Elasticsearch by the Logstash pod, which preprocessed the flow packets and sent it to Elasticsearch. So this is the dashboard view where you can see some top servers and clients. We can go into some top end view where we'll see top clients and top servers running in the cluster. Of course, you can order that by packet counts, byte counts, flow records, etc. You have the abilities of filtering. For instance, we can look only at the DNS traffic. We can go into flow view where we see on this nice graph exactly which pod talks to which one in the cluster. Again, you can filter out by server, by client, or by service. There is geo-IP functionality as well. In my cluster, it does not show anything in here because all the communication is node local. But in case that you would have some clients accessing the cluster from the internet, you would see from where the clients came. We have traffic details in here where we can look into individual client and server flows in more detail. We can browse bit rate, packet rate between clients and the servers. And the last one would be the actual flow records that are stored in the Elasticsearch, which is the base data from which we are generating those views. Let's open some. So this was communication between this client IP address and sorry, it was, yeah, it came actually from the host itself and it went into DNS pod. So this is pretty much the raw flow data. You can use that to build your own dashboards in Kibana in case that you are interested in something else that I have just demonstrated. That's easy. Since all the data is in the Elasticsearch, you can use all the features of the Elasticsearch to build your own queries into the database and views using Kibana. One more thing, I had this on one of my first slides. This is actually the Grafana. So these are the metrics exported by the Contiv-VPP CNI. You can see now that I played a lot with Kibana and Elasticsearch. There was spike in the traffic from Kibana to Elasticsearch. Okay, and now let me go back to my presentation. So what I just demonstrated is just a proof of concept, pretty much. It was a one-node cluster with one Logstash instance, one Elastic instance, and one Kibana instance. In larger clusters, you would actually want it to have the Elastic clustered so that it can handle all the flows. The number of flows that are coming from VPP to Logstash can be quite huge in clusters with heavy workloads. So in that case, you would actually want to have Logstash pod running on each node so that the flow records do not have to travel between the nodes. Of course, you don't have to cluster Kibana. That's just user interface. One instance is enough. Another possible enhancement would be usage of the MEMIF interfaces between the VPP and the flow collector. As I already mentioned, MEMIF interfaces allow packet to traverse between the VPP and the pod through shared memory, which should save a lot of processing in the kernel. For that, we would need to have a flow collector that would be modified to use MEMIF. And one candidate for that may be a GoFlow, which is a flow collector in Go. Since for the MEMIF, we do have a Go library, which is able to talk to VPP, that can be easily integrated together. And also, what you could do is, if you have all the data stored in Elasticsearch, you can export some more metrics, some specific metrics that would be interesting for your particular deployment into Prometheus in order to have alerts that would be interesting for you. Of course, because Prometheus supports Elasticsearch as a source for the data. Okay, that's all from my side. If you have any questions. Feel free to ask.
What plugin are you using for trying out to do your VPP? Are you using DPDK or?
Yeah. So if you need multi-node deployment with VPP using the Contiv-VPP CNI, you usually want to use DPDK interface so that the packet can be grabbed from the NIC into the VPP process directly bypassing the kernel. If your node or VM or server does not support DPDK enabled interface, there are options for doing that through the kernel. You can use AF packet to grab the packets from the interface that would be normally connected to the kernel.
Any more questions? Surely somebody right at the back has a question. You can watch me run. Oh, one at the front. Thank you.
Hi, I have a question regarding managed Kubernetes solution. How does it work with managed like GKE? Or you need to set up the VM there, or what do you need to do?
So the CNI Yeah, one thing of the solution is the CNI. I use Contiv-VPP CNI. I'm not saying that it's the only one CNI that supports IPFIX. I could imagine enabling it in others, for instance, by using some Unix tool, some daemon that is able to export the flows. But for the Contiv-VPP CNI, you can deploy that in some managed clusters, but you need to do a little bit hard work yourself.
And it requires a physical CPU? I know DPDK requires a CPU?
No, it can be virtualized. The most important thing that you need is the support for the NIC if you need higher performance. But as I said, that can be bypassed as well, but you would get much lower performance.
Okay, thanks a lot.
Okay, thank you.
Yeah, thank you.